Welcome, good evening everyone. My name is Gord Tanner. I'm from Waterloo. I'm here just, I had a question that I kind of asked myself a lot, called, why would we ever build a distributed computing platform in Node? So to start off, basically who am I? My name is Gord Tanner. You can follow me at Gord Tanner on Twitter. I am a co-founder and CTO at BitHound. So a little context about who BitHound is. BitHound is a small startup. We're in Kitchener, Waterloo, founded by myself, Dan, and PJ Celestru. We actually have an old house we've renovated in downtown Kitchener. So it has a nice two-tier porch. It's just kind of this nice home feel that we really wanted to have. So we have a little living room and chalkboards everywhere. And for the 2 months we have summer, we can work on the porch. But what do we do at BitHound? So all of us as developers, we know that as we're working, we generate a lot of data. Through the issues we create, the bugs we open, the bugs we close, the code we write, the tests we run, there's a wealth of information that we just generate inherently by the work we do. What we're doing at BitHound, we're taking all that information and distilling it down to basically build up a kind of knowledge or health or a quality score for your code. We just want to build something that allows teams to have a common ground of communication between managers, executives, and developers to reference the same things in the same areas of code that needs to be focused on, the same areas of code that needs to be worked on. So we knew this, like going into this project, we knew inherently that there was a problem. If any of you have run your own tools, your own unit tests, you've run your own linting, you've run your own static code analysis, there's inherent time it takes to collect and work on this data. So running lint in some cases could take upwards of 30 seconds. So imagine this is one facet of what we're analyzing. There are many things we're looking at. There's just a lot of information. We knew from the very start that this was going to be a problem because waiting sucks. We want to be able to have people come to our site, click sign in, click a repository, and get information as fast as possible. So we knew right from the get-go that this was going to be a concurrent problem. The only way we could kind of work on this was to do things in parallel, to break it up, to do it in a distributed environment, just from the inherent nature of what we were working on. So, quick little background when I say concurrent. So concurrency from Wikipedia is just the idea that you have your computations or calculations executing simultaneously and the potential for those to interact with each other. So why JavaScript? That's the question you can usually get. So JavaScript is a single-threaded web platform, not known for its concurrency, if any. So there are hundreds of languages out there, such as Go, Haskell, Scala, or there's infinitely more better choices than JavaScript. But with any real technical choice that you make, there's usually history. There's usually a little bit of influence from your team. So I'd like to introduce you to a company called Tiny Hippos. It was founded by Dan Silvestru, PJ Celestru, Brent Lindner, and an employee developer called Gord Tanner. So you can tell that we're very creative. We're not marketing people, so we have an algorithm for building company names. We have a unit of measurement and an animal. So Tiny Hippos, BitHound, it kind of works. So we were a consulting company. We were doing bundled apps. So the idea was we worked on HTML5 apps, bundle them with PhoneGap, Jill, Whack, a bunch of platforms back then, ship them as native applications on the phone. But there was a problem that we kind of had, where the tools really sucked back when we started doing this. There was nothing out there. It was you would work in HTML5, compile links, statically upload it up into a simulator, and eventually you could like look at what your app would look like, which would look nothing like what it did in the browser. The tools sucked. So we built Ripple. It was a tool we used internally, eventually became our product. But Ripple was an emulator that ran in Chrome as an extension, 100% in JavaScript. If anyone who's worked on Chrome extensions before, JavaScript's all you got. JavaScript, HTML, and CSS. So we wrote a rather large code base entirely in JavaScript. We were one of the first, we kind of first played around with modules. We built our own module loader in web JavaScript as one did back then. But we learned quickly on how to manage a large JavaScript project. We had a pretty good in-house experience with working on JavaScript. So with that being said, when we wanted to start BitHound, we went to like, okay, we're going to do static code analysis, dynamic code analysis. We instantly decided to go for the horrible pun that I always hate saying, eat our own dog food. Let's do this in JavaScript. Let's do it on Git. Those are the two things we know. Those are the things we've worked on. Rather than trying to start in something like Haskell and not writing tools for Haskell, but it works. So to start off, we're doing this in JavaScript. We're doing it in Git, so we can analyze our own code. We can kind of use the tool itself to hone the building of the tool. So back to concurrency. So another core tenet of concurrency, so when you start splitting your tasks, when you start splitting these computations, you can run these computations in multiple cores on the same chip. You can have it time-shared threads on the same processor, on separate physically separated processors, or even physically separated machines. But you always come down to the kind of quote at the end there, the potentially interact. And that's where the headaches come in. That's where you kind of get stuck with distributed computing. And there are kind of two competing kind of ways of handling concurrency and communication. So the first is shared memory, and it's one that everyone's probably familiar with. The idea that you'll have some shared location that you can interact with and alter. So someone would store your data over here, and you'll alter it, and then someone else can come in later, read it in, get the shared state, and that's how you interact. The idea is that you have to have some form of locking around it. So everyone's familiar with mutexes or semaphores or monitors, but the whole concept is that you become thread safe for interacting with this shared memory location. And one of my first jobs, I was doing telecom statistics gathering, and it was a multi-threaded system, and spending a bunch of weekends trying to diagnose deadlocks sucked. So the whole idea is it's hard. There are very, very narrowly fine-grained controls for concurrency and for interaction, but they're hard. It's really hard to wrap your head around all the potential interactions that can happen in a multi-threaded system sharing locations. So the other kind of way that kind of grew out of concurrency problems was message passing. So it was kind of exemplified by Scala, Erlang, but the idea of rather than altering a physical memory location, you exchange messages. And the message exchange is what you use to interact with other processes. So these message passing can be synchronous, asynchronous. You can have them durable messaging. You can have unreliable, kind of the fire and forget kind of message passing. But what this added was a really easier to reason about way of communicating amongst your processes. It was just inherently easier to kind of wrap your head around the concept of sending a message off to someone somewhere and then them sending a message back. And all the interactions were handled through this sharing of messages. It just was a much more robust, kind of easier to reason about message passing. And the beauty of this was that JavaScript had this. If we all remember, we know where JavaScript came from. JavaScript was a programming language built to run in browsers. And when it was first kind of written, and kind of idea was that The browser developers and the browser, people who are writing the browsers, their first gut reaction was, you want those people who have been making these websites to get into my rendering pipeline and run their own code? No browser developer in their right mind would let us get into that rendering pipeline to make their browsers slower. So they built into JavaScript as this single-threaded, event-driven, message-based language. So we are all used to DOM events. We're used to the eventing systems built into it. Everything was evented in JavaScript because we were running in a single process and being signaled from a vastly more complicated system. And so when Node came along, Node, if you take the definition right from Node.js.org, the idea was Node is for building scalable network applications that are data intensive across distributed devices. And if you really think about that, everything in that statement is talking about concurrency. Everything in that statement is talking about distribution. So the way Node kind of got into this was the idea of the cost of I/O was heavy. If you ever were to look at any process out there and kind of time share it, you look at I/O is where you spend a lot of your time. May it be reading from the cache of the chip, from your RAM, from your disk, over the network, over conference Wi-Fi, which never works. The idea is that time is spent in I/O. And so what Node did, which was actually really, really genius, was use the same kind of idea what we're used to as JavaScript developers with eventing. So with asynchronous I/O, the idea is there's a thread pool in the background handling all that really fine-grained interactions of mutexes and locking. And any call we make that we need to do that requires I/O, we just send it off an event. It gets put on the thread pool, processes it, comes back into the event queue, stacks up, and the event loop is just sitting there in one single process, picking these things off and feeding them into our event handlers, into our methods, into our objects. So really kind of genius when you think about it, but it doesn't come without its costs. So because our code is running in the same process as the event loop, it didn't take long for people to realize that there's a problem with this. So this is a very, very popular example called Node.js is Cancer. We're taking a Fibonacci loop and this kind of response.write, response.end, run Fibonacci for 40 instances. It loops over them. Not really an optimal solution, but gets the point across that your code is going to block that event loop. It's going to slow everything down. It's going to make your request per second go down because JavaScript has one thread. We can argue night and day if this is awesome, if it's not, but there's an inherent beauty to this. So I bring up this quick example. Can everyone see that? So this is using a library called async. The whole idea is that I have an async queue. I have about, all it does is get a callback. It has, I'm going to run 5 concurrent listeners on it. So as I push items onto this queue, it'll pull them off, 5 processes working. It'll push it to this numbers array, wait a little bit and call back. And I have a thing run right after that I, from numbers 1 to 10, can currently push them onto the stack. And at the end, when I'm all done, I'll log the numbers. So to run this, all I did, I printed an array. Anyone notice anything really interesting about the array? It's in order. That's odd. I didn't do anything other than this code in a lot of other languages would do. It's like, oh, well, what if that left somebody a fluke? What if I go up to 100? Turn my sound off. Go up to 100. Takes a little while because I only have 5 workers working on this, but it's the same idea. I can even bump up the number of workers to 500. But the whole idea is there's only one thread. There's only one process running. There's no possible way code can be re-entrant. There's no possible way that you can really shoot yourself in the foot. Don't ever rely on this behavior. This is just kind of written to kind of give you the visualize that there's only one line of code running at a time in your Node project ever. So you can write concurrent code in JavaScript, and you don't have to think about a lot of these concurrency primitives. So I know, am I gonna create another distributed framework? If any of you go to Node.js or NPM and you search for distributed, you'll notice about, about 2,000 packages, all averaging around 0.0.1 to 0.0.3, might have 2 commits on them, of someone out there discovers that Node.js is really awesome for doing distributed computing. Am I going to be yet another person releasing a distributed framework? No. No, sorry. It is an extremely personal choice. All I can say is pick the tools you know, pick the languages you like build out the processes that you need. That being said, this is an incredibly technical conversation. We open sourced this kind of wrapper around our distributed platform called Farm. So if you go to github.com, bithhoundfarm.bithhound.io, that's the actual component we use to handle all our orchestration. It's just there. I figure someone else might be able to look at it and kind of get an idea of how to abstract out this distributed messaging. So you can use it, no guarantees. It might grow into something awesome later. So now that I have these individual processes, I needed a good way to send messages around. And so I went on a technology called Zeromq. So the beauty of Zeromq is that it looks exactly like a networking library and behaves like a networking library, but underneath it's actually a concurrency framework. So we've all used WebSockets or TCP sockets in the past, and we're familiar with the concept of writing and reading the sockets. It's something we're used to, but there's something awesome when you kind of start thinking, well, what an actual Zeromq socket is. It behaves like we're used to. So the core tenets to Zeromq sockets is they carry atomic message across transports. So the atomic delivery of messages means that they're going to get there eventually. Whether you fire the socket before the other end wakes up, whether there's a disconnect in between, and also the transports are pluggable. So I write to a socket the same as if it's a TCP, an inter-process shared memory, or an in-process socket. It's all hidden. It's all kind of compiled, run configuration time. So I can easily change throw something on a socket that communicates with something running in my process versus something running in another data center. Also, the sockets are built that you can connect them together end to end in kind of overall concurrency patterns, such as request replies. So the idea that I can send out a request, someone's going to reply, and there can be hundreds of people doing the request and only one process replying, or one process requesting and hundreds replying, or hundreds of processes talking to other hundreds of processes, and all that routing is handled for us. There's publish subscribe, so the standard of venting style socket types, fanning out and fanning in, so sending a bunch of messages to a socket and having that socket round robin deliver them to all the other people that are listening to it and gathering results back and sending it to the person that sent that request. But all those concepts are hidden, and all you're doing is writing to a socket. So once we have this kind of ability to send messages, ability to spawn up instances all over the place, we had to kind of sit down and go, what are the tasks that we need to process? We're like, oh, I have a repository out there and I want to analyze it. And the repository has commits and I have files in the repository. And obviously I'm going to distribute it certainly. The whole concept is think about what you're going to break up and then just forget it because you're wrong. Build your system in a way that's flexible. Build your system in a way that you can adapt, because you're going to get it wrong a lot. So the key is try to understand your project. Try to assess what you actually need. Just because you can distribute something, just because you can do something in parallel, doesn't mean you should. And lastly, only then start to define your tasks. And also define them in a way that you can change. You can get your tendrils in and something. So that being said, I was like, this is great. I built up a thing, so I kind of built these process kind of like frameworks that can spawn up a master process. Its job would starting job, it breaks down the works, it listens to the status. So I throw that on my web servers, and then that's all they do. It's like, oh, I need to analyze a repo, or I need to do X, do Y, and then I spawn up these slave processes that would just sit there and work on the job. That's all they did, and life was good. The whole idea was just message passaging and just transparent. The idea that hey buddy, can you do this thing for me? And we just kind of send it off there, and they come some, sure, here you go, what's up? It was great. It was totally transparent. I didn't even know how many slave processes were out there. The slaves actually didn't really know where the master was. It was just kind of someone told it to do something. It was really awesome. And also, once I started having more of these slave processes, the whole concept, the master process would kind of go, oh my gosh, I have this bunch of things to do. So I have a list of commits and send it off, and a bunch of slaves would pick them up individually, work on them, and send back, all right, this is really cool. Go back. So then I hit something interesting. I had the master process. Imagine a request coming in, and I'm like, okay, cool, I want to analyze a repo. All right, in my web handler, okay, well, clone the repo. Okay, now I cloned it. All right, well, now I need to find out all these commits and then send those commit messages out and kind of come back. So it got to the point where I'm like, no, I really don't want my master process to do this. And then I didn't want my master web handler to become this giant orchestrator handling, sending, and receiving all these messages. So I was like, oh, well, let's get my slave process to kind of go, oh yeah, I have this repo, and builds up a bunch of messages and sends them out, and other slaves would work together and pull them all back. It was really kind of cool. But I had an ethical dilemma. Because what was the difference at the end of the day between my master and my slave at this? There was, at the end of the day, they're both sending jobs off. And the key was there is no difference. Major rewrite. So rewrote things. There is a little bit of nuance in this, that there are some workers out there who really only like to tell people to work and don't actually want to do any of the work. I'm sure we all have examples in our lives. So I made everyone's a worker in our process farm. Everyone can spawn up work. Everyone can tell people work. But you can opt in if you want to actually do any real work. So I made a wrapper library around this. This is kind of what farm is. This is that example that we open source. So I call it farm because I don't know. I really don't have a good. I just compute farm. One of the reasons why I didn't release a distributed framework is a lot of more smart people and cleverer than me with naming kind of got there first. If anyone can actually think of a good name for this that doesn't sound obscure, that'd be cool. So requiring a farm, and the whole I broke it down into these kind of overall orchestration primitives. So if you have a task, you farm.jobs.send, give it a task object, and you give it a callback with an error and a result. We're all used to that in Node. If you have a bunch of things to work on, you don't really care the orchestration of them, send farm.jobs to distribute, just send that array into it, and at the end, you have a function and result of all of those happening in parallel. Something that actually kind of came into fruition while we were working on this was this farm.events.publish and subscribe. It was this, we really added in because we had this pub/sub type in Zeromq, but once we added this in, the ability to have hundreds of processes out there have a single event emitter that you can publish and subscribe to events to became a really powerful tool that we started using for statistics monitoring, for logging, for global cleanup jobs. So we can send out hey everyone, there's a deploy happening in 10 seconds, start cleaning up your jobs, or just overall kind of events that you want to have in a global scale. And then lastly, the concept of the worker. All a worker is you give it a callback. That callback takes a task, and you have a callback you call when you're done. It's all kind of primitives we're used to in Node. And it's the simple act of adding that callback adds you to the queue of potential workers. So, launch day. Built this all out. We're like, oh, we're going to launch this to our, like, we had a limited run, about 50 to 75 people we wanted to show it to. As you can tell by Twilight Sparkle, it did not. It was not ideal. Because you learn really well that what works well on one machine doesn't always work well on 200 or more machines. So our dev environment up until that point was on our laptops, on maybe a Ubuntu machine we had. So we'd fire up our web app. We had this little broker process that would handle a bunch of stuff. We'd fire up our workers. We fired one up for every core, so we're distributed. Worked really well. But production, a bunch of web apps, a bunch of brokers, hundreds of machines running hundreds of worker processes. All those assumptions we made about sharing, all those assumptions we made about how these, how we can work on things. So imagine when I send out hey, 100 commits, go, and I have 500 workers. What are the odds of one of those workers happening to get an instance where they already cloned it on? 0. So we had a request would go out. We would clone a repository every single commit. A little slow. So all I can say, for the love of God, just pick a tool and build in a distributed environment. We picked Vagrant. It's a really awesome tool. Whole other talk to give it in. It just allows you to have deployment kind of style VMs that you can destroy and bring up and down. So pro tip, if you're developing a distributed application, develop it in a distributed environment. So we just have our setup. We have local dev. We have 2-3 slaves, our app server, so that now when we're developing, it's working exactly like it does on prod. So that all of the processes are running in machine isolation. It just caught a lot of those assumptions we made. And this is a term I learned from our DevOps guy. He kind of was as he was sending stuff up, he kept referring to oh yeah, that's a cattle machine. And and this thing I can kind of think, we all have our laptops, we all love our laptops, we put stickers on them, we load them all up with our music. They're very important to us. But you're AWS instance out there named 0337 US East large. You don't really care about that process. It's a cattle. It's there to do work for you. When you're in distributed computing or in distributed processes, everything is cattle. You shouldn't have any part of your system that you care about running, you care about existing. Treat everything as cattle, be it an instance, be it a physical machine, be it a process, be it a job that you send out, a message you send out. Treat everything as expendable, and your life is going to be much easier. Because failure is always going to happen. It doesn't matter how robust you build this, things are going to break. If you send out a message and it doesn't come back for a while, assume it's dead. Kill the entire process. What does it matter to you? You'll start up a new one. Because what you're going to end up with is almost this Rube Goldberg machine process in the back. So we have this pretty nifty command line. Actually, the back-end process of BitHound is actually a bunch of kind of little command line pieces put together. We start up services, we send messages, we view state. But the whole concept is all these tiny little pieces that all work together. We can push messages along. We can find a state of a message. We can spawn up more instances. We can spawn down instances. It's a giant Rube Goldberg machine, of which you are part of that machine. The whole concept of this giant distributed complex computing platform is that any part of it, you want to be able to get your tendrils in there. You want to be able to find a job that's kind of stuck in the queue and go, oh, that's really odd. Okay, I'm going to run this script and bump it along. Or, holy crap, our queue depth in this part is really kind of crazy. Okay, I'm going to spawn spot price up 100 Amazon instances and just have the processing of that part beef up for a little bit until we get that through. But you want, as you're building these systems, as you're kind of thinking about these tasks, think about the idea that you're going to want to get your fingers in there to keep things rolling. Because they're going to break, it's going to be hard, but you'll kind of get in there. So, wrap this all up. At the end of the day, why the heck would I pick Node? Why was Node an actual really good platform? Well, there's a couple things. The reference here is it ended up being an extremely good glue language. As we were writing these processes up, we would have cases where it's a little too slow to like analyze all this. Okay, I'm going to like shell down to like bash and awk, which is extremely good stream processing. I can glue together all these disparate services. Also, concurrency primitives in Node are beautiful because there are no concurrency primitives in Node. You can develop these systems, you can bring them up, you can bring them down, you can exchange messages without really like caring a lot about the overall distributed problem of it. So last thing is thanks for coming. We are a startup. We're like this launched our open beta, so we analyze JavaScript code right now. We'll analyze your dependencies, figure anything out of date. We'll look at like static code analysis. We're building this tool up for JavaScript developers because we are JavaScript developers. We want to build the best tool. We want to help everyone build really awesome Node and JavaScript projects. So I invite you all to kind of sign up, just give it a try. You can get in touch with me. I'm Gord at bithound.io. You will get in touch with us if you start communicating. We're a small company. But thanks for letting me talk here. I think I have time for a few questions. But thanks. Yes?
Can you elaborate a little bit on redundancy, or talking about how everything should be cattle, basically, and be able to disappear? So when that happens, like, how are you first off noticing that, and then how are you rewriting the task with that slave?
Okay, so the question is about redundancy and the concept of treating everything as cattle, and how do you handle like restarting things. So the idea is, we have a lot, like through that pub sub bridge that I mentioned, constantly while things are running, we're just sending out updates, like, oh, I'm processing this message, I'm processing that one, I took this one, and we'll kind of monitor the counts and the queue depths. And literally, if we start to see like a certain process that's just sitting there, like that's been in that state for a while, we'll just kill the process. We send out a message out there and go, you're done. Sorry, you're done. And we'll send out that message again and see if someone else will start processing it. When they start processing, monitor it and go, okay, that one worked. And the whole concept of pest versus cattle, if it worked, yes. And then invariably, some developer out there is going to go, why did the other one work? And like the concept is I don't care, because computering is hard. Is the answer. So that's kind of the idea. Is you just want to be able to monitor. You want to keep monitoring on your queue depths. Keep monitoring. If anything breaks, fail out the process fast. Get it back in your queue. Send it again.
I have many questions, but maybe just one more. So then, are you killing just the process, or are you killing the server if that's happening?
Depends on the severity of the error. The key thing, like with Vagrant in our developer machines, like every once in a while we'll have a developer go, this isn't really working, and I'm like, oh, okay, well, did you Vagrant destroy and Vagrant up a new instance? They're like, well, no. I'm like, okay, do that. And they'll do it, and like, oh, it works now.
Restart your computer?
Yeah, it's essentially like, rather than restart your computer, I'm like, okay, well, destroy your computer and get a new one. And the beauty is, because the same scripts we use in production are the same, to new up a new instance are the exact same ones a developer uses. So these aren't scripts that like are never used. Like, so that's another key thing is like make it so when you make a new instance, it should be a universal instance. It doesn't matter whether it's a developer instance for development, AWS instance, you're viewing it up on your own hardware. It should all run the same scripts. It should all provision the same way.
When you got rid of the idea of a master, did you end up with broadcast like avalanches? You're basically, now you have to tell everyone in the network your state. You have to tell everyone what's going on.
A little bit. The idea is you want to keep your messages very atomic in the way that, like timed requests essentially. So if a request comes in, process this repo, we'll send out like a message out quickly, and it comes back quickly and starts up a state, so that anyone else that can come in will just join that session. And we'll use rather than having the message process this repo and that message comes back when it's done processing the repo, we kind of go process this repo and it comes back and say, yeah, you have a ticket and it's off there running in a long running process, and that way if someone else comes along, they just join that session to get the same idea back. That's kind of how we handle some of those awkward, like someone sends in like 8 repository requests, and we all kind of just end up joining one long running process.
I have one question. Why did you choose Zeromq as your backend transport for your messages? I mean, I don't know about Zeromq, but I know that it's not particularly durable, but it could be wrong. So do you have critical operations that fail, like some sort of hardware issues, and you're using Zeromq in your backend?
What I liked about Zeromq, and it's inherently it's fast. It allows you to kind of build up the network topology you want. So it's brokerless. So there isn't like the concept of like RabbitMQ or like some of the other ones where you have this giant service orchestrator. The idea is like I can route messages machine to machine if I need to. I can actually make it so that like I'm sending these messages across here, and as far as I'm concerned, I've been talking to this one machine off, but then all of a sudden I need to like route it differently. Without changing any code, that is now going to another process that broadcasts it to a bunch of them. And I just really like the flexibility of it. It's kind of that like ability to build my own messaging like platform organically once I made these decisions without having an overarching broker and going through the headaches of